Radio pulsar binaries prove that Einstein was at least 99.99% correct. Researchers have conducted a 16-year-long experiment to challenge Einstein's theory of general relativity. The international team looked to the stars, a pair of extreme stars called pulsars to be precise, through 7 radio telescopes across the globe. Credit: Max Planck Institute for Radio Astronomy. More than 100 years have passed since Einstein formalized his theory of general relativity, the geometric theory of gravitation that revolutionized our understanding of the universe. And yet, astronomers are still subjecting it to rigorous tests, hoping to find deviations from this established theory. The reason is simple. Any indication of physics beyond GR would open new windows onto the universe and help resolve some of the deepest mysteries about the cosmos. One of the most rigorous tests ever was recently conducted by an international team of astronomers, led by Michael Kramer of the Max Planck Institute for Radio Astronomy in Bonn, Germany. Using 7 radio telescopes from across the world, Kramer and his colleagues observed a unique pair of pulsars for 16 years. In the process, they observed effects predicted by GR for the first time, and with an accuracy of at least 99.99%. In addition to researchers from the MPIfR, Kramer and his associates were joined by researchers from institutions in 10 different countries, including the Jodrell Bank Center for Astrophysics, the Arc Center of Excellence for Gravitational Wave Discovery, the Perimeter Institute for Theoretical Physics, the Observatoire de Paris, the Osservatorio Astronomico di Cagliari, the South African Radio Astronomy Observatory, the Netherlands Institute for Radio Astronomy, and the Arecibo Observatory. Pulsars are fast-spinning neutron stars that emit narrow, sweeping beams of radio wave. Credit: NASA's Goddard Space Flight Center. Radio pulsars are a special class of rapidly rotating, highly magnetized neutron stars. These superdense objects emit powerful radio beams from their poles that create a strobing effect that resembles a lighthouse. Astronomers are fascinated by pulsars because they provide a wealth of information on the physics governing ultra-compact objects, magnetic fields, the interstellar medium, planetary physics, and even cosmology. In addition, the extreme gravitational forces involved allow astronomers to test predictions made by gravitational theories like GR and modified Newtonian dynamics under some of the most extreme conditions imaginable. For the sake of their study, Kramer and his team examined PSR J0737's 3039 AB, the double pulsar system located 2,400 light-years from Earth in the constellation Puppis. This system is the only radio pulsar binary ever observed and was discovered in 2003 by members of the research team. The 2 pulsars that make up this system have rapid rotations, 44 times a second, once every 2.8 seconds, and orbit each other with a period of just 147 minutes. While they are about 30% more massive than the Sun, they measure only about 24 kilometers in diameter. Hence, their extreme gravitational pull and intense magnetic field. In addition to these properties, the rapid orbital period of this system makes it a near-perfect laboratory for testing theories of gravitation. As Prof. Kramer said in a recent MPIfR press release, "We studied a system of compact stars that is an unrivaled laboratory to test gravity theories in the presence of very strong gravitational field. To our delight, we were able to test a cornerstone of Einstein's theory, the energy carried by gravitational waves, with a precision that is 25 times better than with the Nobel Prize-winning Hulse-Taylor pulsar, and 1,000 times better than currently possible with gravitational wave detectors." Artists' impression of the path of the star S2 passing very close to Sagittarius A, which also allows astronomers to test predictions made by general relativity under extreme conditions. Credit: ESO/M. Kornmesser. 7 radio telescopes were used for the 16-year observation campaign, including the Parkes Radio Telescope, the Green Bank Telescope, the Nankai Radio Telescope, the Effelsberg 100 EM Telescope, the Lovell Radio Telescope, the Westerbork Synthesis Radio Telescope, and the Very Long Baseline Array. These observatories covered different parts of the radio spectrum, ranging from 334 MHz and 700 MHz, to 1,300 to 1,700 MHz, 1,484 MHz, and 2,520 MHz. In so doing, they were able to see how photons coming from this binary pulsar were affected by its strong gravitational pull. As study co-author Prof. Ingrid Stairs from the University of British Columbia at Vancouver explained, "We follow the propagation of radio photons emitted from a cosmic lighthouse, a pulsar, and track their motion in the strong gravitational field of a companion pulsar. We see for the first time how the light is not only delayed due to a strong curvature of spacetime around the companion, but also that the light is deflected by a small angle of 0.04 degrees that we can detect. Never before has such an experiment been conducted at such a high spacetime curvature. As co-author Prof. Dick Manchester from Australia's Commonwealth Scientific and Industrial Research Organisation added, the fast orbital motion of compact objects like these allowed them to test 7 different predictions of GR. These include gravitational waves, light propagation, time dilation, mass energy equivalence, and what effect the electromagnetic radiation has on the pulsar's orbital motion. The Robert C. Byrd Green Bank Telescope in West Virginia. Credit GBO/AUISF. This radiation corresponds to a mass loss of 8 million tons per second. He said, while this seems a lot, it is only a tiny fraction, 3 parts in 1,000 billion, of the mass of the pulsar per second. The researchers also made extremely precise measurements of changes to the pulsar's orbital orientation, a relativistic effect that was first observed with the orbit of Mercury, and one of the mysteries Einstein's theory of GR helped resolve. Only here, the effect was 140,000 times stronger, which led the team to realize that they also needed to consider the impact of the pulsar's rotation on the surrounding spacetime, aka the Lenz-Thirring effect, or frame dragging. As Dr. Norbert Wex from the MPIfR, another main author of the study, this allowed for another breakthrough. In our experiment, it means that we need to consider the internal structure of a pulsar as a neutron star. Hence, our measurements allow us for the first time to use the precision tracking of the rotations of the neutron star, a technique that we call pulsar timing to provide constraints on the extension of a neutron star. Another valuable takeaway from this experiment was how the team combined complementary observing techniques to obtain highly accurate distance measurements. Similar studies were often hampered by the poorly constrained distance estimates in the past. By combining the pulsar timing technique with careful interferometric measurements, the team obtained a high-resolution result of 2,400 light-years with an 8% margin of error. Artist's illustration of 2 merging neutron stars. The narrow beams represent the gamma-ray burst, while the rippling spacetime grid indicates the isotropic gravitational waves that characterize the merger. Credit, NSF/LIGO/Sonoma State University/A. Simon-Net. In the end, the team's results were not only in agreement with GR, but they were also able to see effects that could not be studied before. As Paolo Freire, another co-author on the study, expressed, our results are nicely complementary to other experimental studies which test gravity in other conditions or see different effects, like gravitational wave detectors or the Event Horizon Telescope. They also complement other pulsar experiments, like our timing experiment with the pulsar in a stellar triple system, which has provided an independent test of the universality of free fall. We have reached a level of precision that is unprecedented, Prof. Kramer concluded. Future experiments with even bigger telescopes can and will go still further. Our work has shown the way such experiments need to be conducted and which subtle effects now need to be taken into account. And, maybe, we will find a deviation from general relativity one day. The paper that describes their research recently appeared in the journal Physical Review X, originally published on Universe Today. For more on this research, challenging Einstein's greatest theory in 16-year experiment, theory of general relativity tested with extreme stars. Einstein proven right yet again. Theory of general relativity passes a range of precise tests. Reference, strong field gravity tests with the double pulsar by M. Kramer et al., December 13, 2021, Physical Review X, DOI 10.1103/PhysRevX.11.041050.